Today we will discuss about the another new method of damping estimate. In the last lecture we discussed about the Kah's damping matrix method, by which we can easily estimate the damping matrix. The coefficient CL is given by this equation as we derived in the last lecture, where the coefficient L for the variable L varying from 0 to n minus 1, where n is the number of degrees of freedom, or J, which can be much lower than n depending upon how much you want to truncate the modes, can always find the coefficients C1, C2, C3 so far, assemble them and corresponding damping ratio in the nth mode will be given with this equation. Again it is varying from L to n minus 1 and or J, whatever we have discussed yesterday. So, if you know the frequencies, you can easily find out the values of zeta in every frequency or every mode. Let us take an example quickly and demonstrate this before we move on to the new method by which I can estimate damping matrix by superpositioning technique. This is another way. So, let us write an example, the same example we will solve. We already have the Rayleigh damping with me. So, let us try to solve this for a Kahi damping method. So, this was the problem given earlier. So, this was taken as K, this was 1.5 K, this was 2 K, and in this problem M was given as 3500 kg and K was given as 1500 kilonewton per meter. We already have omega 1 values with us, which we computed, or you must have computed from different methods. And the corresponding mode shapes also we have. So, all positive, no zero crossing, here 1 zero crossing, and here 1 here and 1 here back again. So, first mode, second mode and third mode. So, when you substitute L is equal to 0 to n minus 1, let us say we will take 3, zeta 1, zeta 2, zeta 3. So, let us try to find out what is C naught and C1 and C2. So, we already evaluated them in the last class separately. So, let us say I will write C matrix is simply A0 M plus A1 K plus A2 K M inverse K. So, mass matrix for this problem we already have. Stiffness matrix I think we should write. Do you have the stiffness matrix with you? Okay, anyway, I think we have it written already. It should be available with you. Okay. So, substituting back in zeta n, so let us say half L equals 0 to n minus 1 AL omega n 2L minus 1. So, 2 zeta, because you know all these values of A0, A1 and A2 will have half as a multiplier. Okay. So, 2 zeta n will become A naught by omega n plus, which I already derived in the last class. We have these expressions with us. A1 omega n plus A2 omega n cube. Now, let us assume that I have 5% damping in all the considered modes for the study. So, the omegas are 11.8. So, 1 by 11.8, 1 by 29.27 and 1 by 44.778. So, A0 and then A1k, A1 omega n. So, 11.8, 29.27, 44.778. The third one could be A2 omega n cube. So, 11.8 cube, 29.27 cube, 44.778 cube. So, let us read one column, or let us say one value. 2 zeta will be A0 by omega 1 plus A1 omega 1 plus A2 omega n cube. So, similarly, I will get a matrix. Now, I want to find A0, A1 and A2. So, it is simply the inverse of this matrix multiplied by this. So, I call this matrix A, let us say. So, find A inverse and multiply with this vector. So, 3 by 1, 3 by 3 and 3 by 1, compatibility, answer. So, can you get me the value of A0, A1 and A2 quick? So, with the calculator easily you can invert 3 by 3 matrix comfortably. So, get me the value of this vector, the coefficient vector A0, A1 and A2, 0.70. Point 00. Can you quickly compare these three values with that of Rayleigh, what we had in the last example? We also had these answers from Rayleigh. Of course, A0 and A1 only, not A2. Point 84. Not. So, it is obvious if you multiply this, because you know A0 which is equal to 0.77 in this case, you know A1 which is 0.003, and you know, of course, you know A2 which you will multiply with this, and this term generally for this problem low significant. So, it is very clear two inferences from this example. One, Kage damping, though it is extending for higher modes, effectively Rayleigh would represent more or less the same contribution from that of Kage. Okay. Secondly, only the first few modes are important in a given MDF system, remaining modes do not actually contribute. Okay. So, modal truncation is a very important method by which we can ignore the modal participation of higher modes. Okay. We need not have to go for n minus 1 modes at all, it is not required. So, Kage was intrinsically working at a higher end contribution of different modes, but whereas in Rayleigh truncated to the initial modes, it was fine. Okay. So, now once you know these values, you know M, you know K, you can perform this as well. You can easily find the damping matrix which is required for this problem, which I am not working out, you can easily find it out. Now let us look at the another method of the same problem, which I am going to do by modal superposition. So I will retain the problem as it is, I will just only rub this part because the example is going to be the same. So by the third method, which is damping matrix estimate by superpositioning. We will try to see this method now. Let us say we know phi transpose, where phi is a matrix, each column of phi consists of each eigenvector or a mode shape. For example, it can be a phi matrix where each one of them is called as small phi. Small phi indicates mode shape, whereas capital phi indicates a matrix. So phi transpose C phi is generally a C matrix. Please note, this is coefficient, this is a full matrix. It is a standard algorithm, okay, where Cn at any nth mode is given by we know this value, okay, 2 zeta n omega n. Let us call C equation number 1, this as 2. So from equation number 1, if you want to really find the coefficient, I must say phi transpose inverse C phi inverse. This is equation 3, because I am pre-multiplying, post-multiplying the inverse of this, so I get identity. I do the same thing on the right hand side, I get this, okay. Now interestingly, if you look at the equation 3, it is very difficult to work out the matrix because you have got to invert two matrices, okay. Equation 3 demands inversion of two matrices, which is difficult computationally. Can we have an alternate method for this? I do not want to invert both the matrices, but still I want to find C. I am only doing superpositioning, that is all, okay. There is an alternate technique available for this. Let us see how. I will rub this part. From orthogonality principle, we know, let us say, what do we know? Phi transpose m phi transpose m phi is m. Equation 4, hey, phi transpose m phi is capital M, fine. Let us first find out phi inverse. Phi inverse, of course, m inverse phi transpose m, okay. Call this is Fourier. Let us now get phi transpose inverse, which will be m phi of m inverse, call 4b. Now this multiplication is easy, 4a and 4b, for simple reasons. M is actually a diagonal matrix, ordinal elements are 0, okay. Once I perform this operation, I am not inverting actually phi, which is difficult. I am only inverting m. Inverting m is very easy because only diagonal elements are there. For example, if your m matrix could be 4, 4 and 3, let us say, inverse straight away could be 1 by 4, 1 by 4, 1 by 3, you can easily do that, okay. Now, by performing the operations of 4a and 4b, I will get actually phi inverse and phi transpose inverse which was required to compute C at equation 3. If you look at equation 3, if I know these two, in terms of this, I can easily find C. Okay? C could be determined by evaluating 4A and 4B without inverting phi or phi transpose. Hence, equation 3 now becomes, which was actually C phi transpose inverse C phi inverse. Now, since therefore phi transpose inverse was m phi m inverse, which was this value from 4B, C phi inverse phi transpose, I now call this as equation number 5. Now, M and C are diagonal. Hence, equation 5 now becomes, I can take this M out, which is common in both cases, summation of n, okay, n, let us use the count n, because we have used n everywhere, to zeta n omega n by normalized mass matrix Mn phi n transpose of M. This is true because this is diagonal, this is also diagonal. This gets set up to this particular value and you get phi n and phi transpose. Equation 6. Now, let us look at this equation. I know the mass value for a given matrix. I know zeta n and omega n. Of course, omega n I know, zeta n I will have to substitute. Okay, 5%, 2%, whatever may be. Of course, I know the mode shapes. I can easily find the transpose of these vectors easily. Pre and post multiply them with mass matrix. I get the damping matrix easily without any inversion. Okay, I am not inverting any matrix here. Let us apply this to this problem and compare this matrix with what we got from Rayleigh and Kage and see how does it compare. Okay? So, let us do this. It has got a very important advantage. Let us say observations. One can include any number of J modes, though there are n modes, J is less than. What does it mean? For your choice, you can select this upper limit of this summation to any J number. One can ask me a question, if n is 3 and j is 2, so therefore you will not have the contribution of the jth is equal to 3 in C. It means the damping matrix will have no contribution of damping ratio from the third mode. Suppose in a given matrix you have only C1 and C2, do not have C3, but you have third mode also, it is implied that the damping ratio from the third mode does not contribute significantly to the overall damping matrix. Okay, damping matrix is dissipation of energy, it is response control, response decay. It has been found to be proportional to mass and stiffness separately, independently, but practical examples and experiments show that they are neither mass proportional nor stiffness proportional. So, Rayleigh suggested we take component of mass and component of K and say A0m and A1k and found out a matrix, and that gave me a liberty of truncating higher modes. But Kage extended that, saying that let us go for higher modes also, but it did not show me significantly. For this example, it is going to be as similar to that of Rayleigh damping. So, this becomes more simple because it does not have any inversion at all, and it gives you a liberty of selecting any number of modes, whereas in this case you cannot do that, you have to keep on evaluating them. See, you came to understand that the contribution of the third mode is not efficient only when you know A2, okay, until then the calculation was on, but here you can easily do the truncation as per your choice anywhere you want. That advantage is there. The second advantage is lack of modes. Lack means absence, lack of modes from j plus 1 to n, because these modes are not present. When I say we are truncating till j, from j plus 1 till n, these modes are not present in my calculation of damping matrix C. So, lack of modes from j plus 1 to n does not create numerical problem. Provided unconditionally stable time stepping procedure is used to integrate equation of motion. We will talk about this unconditional time stepping integration procedure later. There are many methods. If we choose this will not create a numerical problem of deleting higher modes from j plus 1 till n. There will be no problem numerically in this method. So, these two are considered to be great contributory advantages for using modal superposition method for estimating damping matrix. We will apply this concept of equation 6 to this problem and try to evaluate C matrix and see how does it compare with my Rayleigh and Kage. So, for simplicity we will take only two modes because I want to show what is the effect of that. I will keep this as it is. So, let us consider the same example . The example is here, this is the example 3 degree freedom system M1, M2, M3, K 1.5 K, 2 K. We already have omegas and phis for the system. We of course are not going to use this. This is Kage's relation. If we eliminate this is Rayleigh's relation, but I am not going to use this, I am going to use this relation, equation number 6, to estimate damping matrix C. Are you getting the point? So, I have M matrix and of course, I will have K matrix because I do not require actually K. So, there is no botheration about this, I want only M matrix available with me here. Let us do this. So, let us first find C1. Let us substitute C1 and see what happens. In the internal term, let us evaluate this first, 2 times of 0.05, assuming zeta is 5%, 0.05, omega 1 is 11.8 divided by normalized mass matrix 1, we will multiply 3500 later, m phi n transpose, yeah, it means, can you give me what is this value? It is 1.18, no? 1.18 multiplied by 3500, that is the mass value, phi n phi 1 is 1.68, 0.32, 1.68, 0.3. You can see here compatibility 3 by 3, 3 by 1, 1 by 3. Okay. Can you find out this matrix? Can you find out this? Again there is a mass multiplier here, please understand. After this again there is a mass multiplier 3500 of okay. So, do all the multiplication and get me the C1 matrix. C1 matrix. I shall write it down for you, please check. 14.46, 9.83, 9.83. Similarly, let us try to get C2. So, I will substitute the values only 2 of 0.05 because I said zeta will be same in all the modes. Okay. One can ask me a question, why zeta should be same in all the modes? What is the requirement? I know the answer for this, why it is so. So, 29.27, that is my second frequency, divided by again the mass matrix of that value. I am talking about this one, 1 multiplied by m phi 2 transpose, yeah. So, I have all the values because phi 2 I know here, it is phi 2 transpose I can find, mass matrix available here. I will pre-multiply proportional to 3500 in both the cases as I did here, get the value, and I am now writing C2. This is C2. Now, one is not interested in getting the part and parcel of damping matrix, he wants the whole matrix. So, the C matrix will be given by C matrix is now given by C1 plus C2. Now, can you please answer me why it is C1 plus C2? Yeah, why it is C1 plus C2? Why? The whole method is on superposition here. We are talking only about the addition. That is why we started. It is only a summation. C is summation of this. Algebraic sum of n varying from 0 to j. So, I keep 1 to j, keep on adding them. So, it's simple superposition. So, add C1, add C2, get C. Now, I will give you a tougher task. I want to compare the C with superposition, with Rayleigh and Kahe, and tell me which is higher and which is lower. And now we have 3 damping matrices. Okay? So, one should be able to tell me. So, I have another question to you. Now, C3 is missing here. What do you mean by C3 missing here? Initially, the system has 3 degrees of freedom. I think we go back to the first lecture. Do you all believe the system has 3 degrees of freedom? Yes. How can you say that? I am not getting. I am not getting you. I have not heard any one of you. Why are you saying it has got 3 degrees of freedom? Sorry? Is anybody trying to answer that there are only 3 mass points? Is anybody trying to answer there are only 3 mass lumped points? Is it so? But the lumped mass position does not indicate anything about the degrees of freedom at all. But still, in this case, there are 3 lumped mass, and therefore the 3 degrees of freedom is correct. Can you tell me why?
We are considering only 3 independent displacements.
Agreed. But in this example, 3 mass points is a 3 degrees of freedom is correct. Why? The answer is on the board. Sorry? There is no stiffness matrix, the answer is not in the board. Because the mass matrix is diagonal here. The mass matrix is diagonal. It means displacements are measured at the lumped mass points. If you do not get the basics, we will be rounding only. Okay? We will not be able to get through the dynamics at all. I am sorry, but you are not able to get through what you actually want. This clearly illustrates the displacements degrees of freedom are marked only here because the mass matrix is diagonal. This will happen only when x1, x2, x3 are located at the points where the mass is lumped. This was explained n number of times in the class. Now answer me. It has got 3 degrees of freedom, there are 3 frequencies and 3 mode shapes. But C has only contribution in the first and second mode shapes only. What does it mean? Why C3 is not present here? What does it conclude? This C matrix will conclude that the contribution of damping from the third mode is insignificant. It is not the third mode damping ratio is lesser. Please, this is where people misunderstand. The damping ratio is constant in all the modes. Why it has got to be constant? First question is asked, but you have not answered that. It is required because that is what is called classical damping. It should be uniformly throughoutly spread for the entire structure. So, I have zeta of 5% in all the modes, no doubt on that, there is no decrease on that, but still the contribution of that zeta on the third mode is lower. Why? The mode shape is compromising on each other. When you got a positive displacement, you got a negative displacement somewhere, they are compromising. Therefore, there is no dissipation of energy happening because of this vibration in the entire system. Okay. So, if you keep on adding higher modes, you will see that the contribution generally of the higher modes on the damping is decreasing. It is because of the reason people said let us truncate the modes and bring down to 3 or 4, but the number is not a magic number. You have got to justify where should we stop the mode counting. Again it will be related to mass participation factor, because everywhere you see truncation of mode related to mass, truncation of C related to mass, you see here. Okay, mass and mode shapes are very important. Frequencies are also important in this case, but mode shapes are also equally important, because they will tell you what is the effective contribution of that particular vibration mode in the overall damping, because they are compromising. Okay, one is positive, one becomes negative. So, they may compromise on each other in terms of the vibration mode. After all, modes are nothing but relative displacements of mass points at a given frequency of vibration. Okay. So, that is how I do not have to have an influence on C3 on C. So, I have a very small homework for you. You compare C of superposition method, compare this with Rayleigh and Kage and try to compare the percentage error between these, considering maybe Rayleigh as the base. Considering Rayleigh as the base, you can try to find out how much is the error given by these methods. So, this ends the discussion on damping evaluation. Now, as we all understand from these lectures now that higher modes need truncation, there is no need to consider all the modes. On the other hand, if there are n degrees of freedom, you are actually not required to work out omega n's and phi n's, it is foolish, you do not require them. Okay, it is not required. Therefore, classical eigensolver which will give me all the mode shapes and all the frequencies is unpopular, it is not required. And it is because of this Dunkerley is more popular, because Dunkerley at least for sure gives me the fundamental frequency. Stored law is popular because it gives me fundamental and the mode shape also. Influence coefficient method is popular because it gives me the frequencies and mode shapes in order and they are orthogonal automatically. Okay, so if you do not understand these clusters in a chain of lectures, dynamics will become very dry. Applying will look like matrix algebra. You have to relate it to design actually. So, you see here this mode of vibration is not going to contribute to the vibration or mass participation of third mode. Damping ratio is not reduced in third mode, it is same as the first mode, but still it is not contributing. It is only because phi 3 is compromising. Okay. So, higher modes need to be truncated. How do we understand truncation of modes? That is the next lecture which we will address.